Hello, this is Microwave Journal Technical Editor Pat Hindle, and I'd like to welcome everyone to our Technical Education webinar series. This installment is Interference 101. Our special guest presenter today is Robin Jackman, an application engineer with Tektronix. Today's presentation is approximately 35 minutes long, after which time we'll hold a 15-minute question and answer session with Mr. Jackman. You may submit a question through the website at any time during the presentation using the Q&A box on the right-hand side of the presentation window. Please address the questions to all panelists, which is a default setting, and the questions will be addressed at the end of the presentation in the Q&A session. This presentation will be archived and available for viewing later on in the Microwave Journal website in the Resources section. If anyone would like to see more detail on the slides, you can usually click on the large button in the lower left-hand part of your screen. Today's webinar is sponsored by Tektronix, a leading test and measurement equipment manufacturer with products specifically developed for RF, microwave, wireless, and high-speed digital design and verification, including oscilloscopes, spectrum and signal analyzers, logic analyzers, and video and mobile test protocol equipment. Tektronix introduced the world's first mixed-domain oscilloscope with built-in spectrum analyzer, allowing engineers to capture time-correlated analog, digital, and RF signals for a complete system view of the device under test, supporting visualization of the time and frequency domains in a single glance and view the RF spectrum at any point in time to see how it changes with the time or device state. Some of the capabilities of the mixed domain oscilloscope will be highlighted during this webinar with Mr. Jackman, and he'll discuss the basics of interference and why a spectrum analyzer is the best tool for identifying undesired RF signals. At this point, I'd like to introduce today's presenter. Robin Jackman is a senior application engineer at Tektronix with over 25 years of industry experience. He's held a wide variety of positions, including spectrum management, systems design, product development, and regulatory affairs. Robin began his career with the Canadian government after graduating from the Microwave Technology program at Conestoga College in Ontario, Canada. So at this point, I will hand over the presentation to Robin.
My name is Robin Jackman, and welcome to our webinar on Interference 101. This slide here is going to show us a little bit of our agenda for today. For the next 40 minutes, we're going to be talking about interference, talking about spectrum analyzer concepts, talking about measuring and locating interference, and then we're actually going to put through several case studies to talk about everything that we've learned. What is interference? Essentially, interference is associated with degraded performance, some signal that's impacting our system. Is it a coverage issue? Is it a reception issue? Is it an access issue? All of these things indicate interference. The first golden rule of interference is that if you think you don't have it, it's because you just haven't looked. In general, there are three types of interference that are the most common. Co-channel interference is by far the simplest. It's essentially more than one transmitter on the same channel. Many people think that they own a frequency or that they're the only people who have a frequency, but in today's crowded spectrum, just about every frequency we have is being shared by some other person or other service. Adjacent channel interference comes from energy from another transmitter that would be close by. Now, it could be close by in frequency, or it could be close by geographically and be of much higher power. The third type of interference is a little bit more difficult to explain. Intermodulation occurs when we have power or energy from more than two transmitters mixing together to create a spurious product on another frequency. In general, third-order intermod products are the most common, meaning we only have two sources of intermodulation. But it is possible to have more contributors in the intermodulation product. As I stated earlier, interference is essentially associated with unwanted energy. In order for us to understand how the victim receiver is being impacted, we have to understand what a radio preselector looks like. In this graphic here, we can see that the yellow indicates our received channel or our assigned channel. Interference can occur when there's energy inside the preselector of the victim receiver, meaning if there's any energy falling underneath that gray curve, it could possibly impact the performance of the receiver, be it through blocking the receiver directly or actually providing some sort of desensitization. When we want to identify interference, very often people will go to a protocol-based tool to figure out how the system is being impacted. Now, this is a really good way to look at what's happening to the system, but it doesn't tell us what kind of interference we're actually looking at. And that's really where a spectrum analyzer comes in. For 40 years, a spectrum analyzer has been the go-to device for RF engineers to determine what's happening in their spectrum. Today, when we start looking at spectrum analyzers, they generally fall into two categories. We have a swept-tune or super heterodyne spectrum analyzer or a real-time spectrum analyzer. The thing we have to look at is probability of intercept. The concept of probability of intercept is how long does a signal have to be on to guarantee I'm going to see it with my spectrum analyzer. In a swept-tune spectrum analyzer, it is sweeping from low frequency to high frequency, so it has a low probability of intercept. It's in the category of milliseconds. Real-time spectrum analyzers, and up to their maximum real-time span, have a very high probability of intercept, meaning the signal duration is much, much less to guarantee we're going to see the signal. It's actually in the microsecond area. And that brings us to our next section, talking about spectrum analyzer concepts. This is a generic picture of what a spectrum analyzer gives us. Be it a spectrum analyzer from Tektronix or some other company, they all follow the same basic layout: low frequency on the left, high frequency on the right, and amplitude on the y-axis. When we start looking at basic spectrum analyzer controls, frequency, span, and amplitude are the three primary controls that most people manipulate. In this slide here, we can see the start frequency, center frequency, and stop frequency controls of this specific spectrum analyzer. The reference level control is very important to any spectrum analyzer. What we want to do with the reference level control is lower the reference level value until the peak of any signals that are on the display are actually as close to the reference level as possible without an overload condition being exhibited by the spectrum analyzer. So I want to make sure whatever peak is in the display here is as close to this reference level as possible. What we're doing when we do that is maximizing the dynamic range of the spectrum analyzer. And that's really important because spectrum analyzers have a great amount of dynamic range compared to oscilloscopes. They also have a great amount of sensitivity. We start looking at the amplitude scale on a spectrum analyzer. It's actually in a logarithmic format in the decibel scale. And there's a couple of reasons for that. When we think about the logarithmic scale, it actually gives us the ability to see very, very small signals and very, very large signals at the same time. Unlike an oscilloscope that has a linear display, this logarithmic scale gives me the ability to look at very, very fine signals down here. There's a general rule of thumb on the logarithmic scale. For each change of 3 dB that we have, we either see a halve or a doubling of the power. And that's pretty important because if you think about it for a second, if we're adding 3 dB and we're doubling the output power, that means a very small change on the display equals a very large linear change in the output of a signal. On this slide here, we're showing the resolution bandwidth control. The RBW control is a filter by which we look at the spectrum within the display. It allows us to discriminate smaller or larger signals based on this resolution bandwidth value. But it's not without a cost. When I think about resolution bandwidth, you see here on the left-hand side, if my RBW is too wide, I'm going to miss smaller signals that might be close in to a larger signal. By extension, if I have a very narrow resolution bandwidth, I can easily discriminate two signals that are close together. However, be it a real-time spectrum analyzer or a swept-tuned spectrum analyzer, if I put in a narrower resolution bandwidth, I'm actually going to slow down my spectrum analyzer, meaning I have to have a longer signal duration to guarantee my probability of intercept. So now we're going to switch over to a video of a basic spectrum analyzer display. So we can see here some basic activity in the 2.4 gig ISM band. When we start looking at the speed of this spectrum analyzer, looking at this signal, the type of detector, the number of traces, the resolution bandwidth set, as well as the number of trace points, all contribute to the speed of the acquisition. So in general, what I say is that swept-tuned spectrum analyzers see less than real-time spectrum analyzers when we're staring at a specific span. Remember, all of these affect the probability of intercept. Depending on that span, that RBW and VBW, and number of trace points, you can actually hinder the amount of information you're going to see. Let's take a quick look now at a real-time spectrum analyzer looking at the same channel. We're looking at the exact same span and the exact same frequency with the exact same resolution bandwidth, but we appear to be seeing a lot more detail. Real-time spectrum analyzers show us low frequency on the left and high frequency on the right. But for each pixel on the display, we keep track of how often we measure energy at that pixel, and we also apply a decay function to that count. So we can mimic the effects of old-fashioned phosphorescent displays. Today, we have real-time bandwidths up to 165 megahertz and real-time transform rates of up to 390,000 transforms per second. That means we get to see a whole lot more than a regular spectrum analyzer display can show us. Now, a point of caution here, when we're looking at the display, the color of the pixel is indicating how often the signal is present. So red, the signal is displayed a lot, and black, there is no display at all. In this particular slide, we can see red of the noise floor and the blue color of the Wi-Fi signal. When we think of real-time displays, we have the ability to adjust not only the color palette, but the persistence. This allows us to see into the signal with a lot more clarity versus a regular spectrum analyzer's max hold display. We have the ability to raise the minimum on the color scale, which allows us to hide infrequent signal. Or, if we wanted to, we could lower the max and emphasize the average that we're looking at. This is going to give us a lot more situational awareness on the span that we're actually looking at. Back in the old days, swept-tuned spectrum analyzers showed us either frequency versus amplitude or amplitude versus time, but not at the same time. Modern spectrum analyzers give us what's called a spectrogram display. The spectrogram display shows us the regular spectrum here, but from a different perspective. It's still low frequency on the left and high frequency on the right, but it's now time on the y-axis, and color is amplitude, red being hot and black being cold. This essentially turns the display into a strip chart recorder and allows us to look at the changes in spectrum over time. This gets really important when we start thinking about interference because we want to be able to log the interference over a specific span. Very often today, we even have the facilities for recording and playing back the data that we record. Got to be careful though. Compared to a real-time display, the color in the spectrogram means different things. Color is now signal strength, red being high and black being low. So now when we think about interference, let's look at co-channel interference first with a regular spectrum analyzer display. Here we can see a peak hold and an average trace looking at a specific span. Looking at the same data, or the same span with a real-time display, shows us there's actually a co-channel signal underneath the real-time signal, or underneath the signal that's being shown here. Adjacent channel interference from a real-time perspective looks a little like this. We can see this rather large digital emission here on the left-hand, or the lower frequency side. We see this signal here right in the very center. We can see that there is a crossover area where the signals are interfering with each other. If we look at it with the spectrogram display, we can see that the power is very consistent between the two frequencies. Although, in the crossover region here, I would anticipate to have a degradation of performance. What's interesting to note is that in the real-time display, we can see two very small spurs right here. Over here into the spectrogram, we can also see those spurs, even though they're almost invisible in the spectrum analyzer portion of the display. That's one of the benefits of the spectrogram. It allows us to see into the noise floor by about 3 dB and figure out or observe non-randomness in the noise floor. So in the next section, we're actually going to talk a little bit more specifically about measuring and locating interference. When we talk about measuring and locating interference, it's all about situational awareness. We have to get a lot of information together for us to figure out if we're seeing a system problem or an interference problem. Understanding our frequency band is the first point. Are we in an assigned frequency or an unassigned frequency? Are we using license-free spectrum or licensed spectrum? What is the band plan of the spectrum I'm using? If you have co-channel services in the same spectrum, that means we're going to have various channel plans based on the class of service. Depending on the frequency and the class of service, we're going to have variable amounts of power. It's possible for us to see massive amounts of power in one portion of the spectrum and very small amounts of power in the co-channel signals in another portion of the spectrum, depending if we're in an uplink or downlink situation. Depending on the class of service, that's going to dictate the modulation. And when we look at modulation today, we have a lot of digitally modulated signals that have much, much higher crest factors versus their analog counterparts. Spectrum shape is also important. This is also equivalent to occupied bandwidth. What is my spectrum signature? We can tell a lot about its signal by its spectrum signature. Environmental effects are probably one of the most difficult features to classify. They change consistently, and there are nearly an infinite number of variables that are constantly changing. Where are we? What is the surrounding buildings like? Are they made of wood? Are they made of steel? Are they made of concrete? Are we in a forest? What time of year are we at? Inside this forest, do we have green leaves? Do we have orange leaves? Or do we have no leaves? One of the things that people ask me most is, when you see a signal on the spectrum analyzer, how am I sure it's coming from my antenna as opposed to coming from inside the spectrum analyzer? There's actually a really simple test. If we put a 2 or 3 dB pad on the input to our spectrum analyzer, the power level that I'm seeing on the spectrum analyzer should decrease by the same amount. If it doesn't decrease by the same amount, then the signal is some sort of spurious product being generated inside the spectrum analyzer. However, if I put a 2 dB pad on the input and my signal goes down by 2 dB, I can be assured that the signal is coming from external to the spectrum analyzer. So when I want to figure out if I'm getting interference or not, the first thing I have to do is log signal activity over time. This is very, very important. We have to figure out when and how often the interfering situation is actually occurring. Figuring out at what time of day it's occurring is important for us to determine where the signal might be coming from. And this brings me to my second golden rule of interference. It's always on when we're not. The basic theory of triangulating a signal is fairly straightforward. We take bearings and measure azimuth and signal strength from 2 different locations, and then plot those on a map. Theoretically, where those 2 bearings intersect on the map is where our signal is coming from. It's a little bit more complicated in practice than in theory, and the first thing we have to understand is some basic antenna theory. This particular antenna we're looking at here is actually made by the pointing. It's a very interesting antenna because it's multiband and directional. You can see here in this plot, this is the way that the antenna actually is receiving the signal. This is its directivity, if you will. Note that the directivity changes based on the frequency range that you're using. This 3-dimensional graph here shows us a very clear picture of what the radiation pattern from the antenna is, which also is the receiving radiation pattern. Note that there is a pattern off the back of the antenna as well. This is called the front-to-back ratio. This is important when we go direction finding because we need to spin around and look from one direction and then in the opposite direction to ensure that the signal we're measuring is coming from the direction that we think. When I start looking at a direction finding scenario, some of the things I have to look out for is, what is the radio horizon of the victim receiver? We need to have the same perspective on the horizon that the victim receiver has. For example, if our receiver is on the top of a 10-story building and we're on the ground trying to determine what the interfering signal might be, we're not going to have a lot of success because we don't have the same radio horizon that receiver has. We have to be very careful when we're in cities. Cities are filled with reflections, and reflections are the bane of existence for anybody doing direction-finding work. The short answer there is to keep moving and get as many lines of bearing as possible. In theory, the more lines of bearing that we have, the smaller the area of uncertainty becomes. And of course, we have to be aware of our antenna pattern. The antennas themselves are not pointing to a signal in a sharp fashion, but have rather a lazy roll to their outside edge, meaning we have to ensure that as we get closer to the target, we actually have to add attenuation to the signal. In modern spectrum analyzers, when we hook up one of these antennas, like the pointing antenna, and we turn on our GPS receivers, it's actually possible for us to look at not only lat and long, but bearing simultaneously, and even add that to a map. As you're taking an antenna like that and you're sweeping the horizon, we have to make sure we don't go fast. If we're going to be using some sort of audible tone, the audible tone in the spectrum analyzer is actually a function of not only the pulse repetition frequency, but also the signal amplitude. And here again is where we actually want to start adding in attenuation. In fact, it's a very good practice to have an external attenuator connected between the antenna and the spectrum analyzer. That way you can easily and quickly add attenuation to the received path. Don't worry about your spectrum analyzer too much. spectrum analyzers have a great amount of sensitivity, more often more sensitivity than we actually need. And as we get closer and closer to the emitter, by adding in attenuation, we're going to minimize the effects of other RF clutter that's around us. And again, don't forget to check behind you. Antennas have front-to-back ratios. So here we can actually see a fairly basic line of bearings on a map, and we can actually see what the target ellipse or what the area uncertainty actually looks like. In this specific example, I can see that my power levels are fairly high, so my area of intercept is going to be very small, meaning I have a higher degree of confidence that my target is actually within that area itself. Once we get into a situation where we're very close to the target emitter, our directional antenna may not be useful for us simply because we're too close to the emitter and the directivity in the antenna gets compromised. At that point, we want to switch over to some sort of monopole or near-field antenna. Note here the pattern of a near-field antenna. A technique we like to use when we get very close to an emitter is actually to go searching for the null, meaning we can turn on our DF tone, but as we manipulate our spectrum analyzer and antenna, I actually try to focus here on the null of the antenna instead of the peak of the antenna. The null is actually sharper and gives me greater directivity compared to using the peak or even, as previously stated, one of the larger, more directive antennas. Putting it all together. So let's look at a case study. Number one, looking at a Wi-Fi network that's experiencing degraded performance. So what do we know about Wi-Fi? Well, an 802.11 BGN network will use the 2.4 gig ISM band. That means the channel band itself is about 80 megahertz wide. Now, being an ISM band, that means we share the services of that band with things like cordless phones, baby monitors, microwave ovens, and even Bluetooth headsets. We know from a band perspective that in the 2.4 gig space we have 11 channels, but only channels 1, 6, and 11 are actually clear. All of the other channels are interstitial. We also know that Wi-Fi is what we call a TDD, or a time division duplex system, meaning we transmit and receive on the same frequency. One of the first things people will do is pull up some sort of SSID scanner to determine, well, maybe I'm getting a co-channel problem. How many access points do I see from my current location? From a protocol perspective, when we turned on an SSID scanner, it says that we actually picked up 3 access points. And then the access point on channel 6, which is in the center of our display here, was actually the strongest signal. Well, let's turn on a spectrum analyzer and look at channel 6, the strongest signal. We can even turn on a triggered acquisition, meaning we're only going to actually take a measurement with our spectrum analyzer when a specific power level has been reached. Using that technique with max hold and average turned on, all appears to be okay still. Now let's look at a DPX, or a real-time view of the same channel 6. All of a sudden, we're seeing a lot more activity. So I can actually see my Wi-Fi signal here in the center, because we're centered on channel 6 from a frequency perspective, but I also see all of these other carriers over top of my signal. The question is, well, why do I see these with DPX and not with a triggered spectrum display? These signals are more than likely very, very fast. Even with a fast triggered regular spectrum display, it's still too slow to see these frequency hopping signals. And we know we're in the 2.4 gig band, and we know that Bluetooth is part of this band. Could these be Bluetooth signals? So let's turn on our signal classification database. In a signal classification database, what I essentially do is declare a region, and you can see that here with the gray box. Inside the region, the spectrum analyzer suggests what might be there. Now, it very handily shows us that, well, the 2.441 gigahertz is actually a Bluetooth channel 39. And when we turn on the Bluetooth curve fit, we can see here that the signal that I'm looking at directly falls underneath the curve. So there's a very high degree of probability that this is actually a Bluetooth signal. Now, if I turn on a longer-term spectrogram, I can see here that there is a fair amount of Bluetooth activity directly on channel. So although both of these classes of service are supposed to be friendly when it comes to sharing spectrum, we see that there is a lot of Bluetooth activity right on top of this channel. Note also that there's two very small spurs inside the span, which could also be causing us a little bit of issue, but we're completely invisible when we start looking at the regular spectrum display. Case study number 2. In a narrowband VHF frequency, we seem to have some sort of system degradation. So what do we know about the VHF land mobile spectrum? Well, historically, it's some of the oldest spectrum that we've been using. There is no defined frequency separation, meaning that there is no minimum frequency split between transmit and receive, unlike what we find at UHF at 800 megahertz frequencies. Depending on where we are in the type of year, we're actually going to get a lot of propagation as well. And the lower you go into the VHF band, the more propagation affects the signal. Another thing we have to be aware of is that VHF frequencies in general are extremely narrow banded, meaning they could be somewhere between 6 and 25 kilohertz of occupied bandwidth. That means those radio receivers are going to be very sensitive compared to, let's say, a WiMAX or an LTE or a Wi-Fi station. Because the bandwidth of the channel is so much less, we're going to get a lot more sensitivity. So here is a picture of my class of service here, and you can see that it's actually an FSK signal. We can see the two defined frequency hops or separations on the FSK. Note here on the spectrogram, though, we can see where there's a momentary point in time where I'm getting another signal directly on top of my own signal. And this signal itself appears to be somewhat wider, but also very, very short duration. And when I see this, the first thing that comes to my mind is intermodulation. When we start thinking about intermodulation, we have to have at least two contributors, sometimes more, but more often than not, it's two. In this case here, we can see as I span out, there are two much, much higher level frequencies in power, but they're actually lower in frequency. In the spectrogram, you can see it. Specifically here, this particular frequency in red is very, very high. We can see here our scale red is about minus 64 dBm. This frequency here is somewhat lower in power. Now, if I classified this as frequency 1 and this as frequency 2, and we look at the intermodulation mix, the question becomes, would a resultant product land on our frequency over here? As I span out and look for a longer period of time, we can actually discriminate an intermodulation product right here. We can see that the power of frequency number 1 is changing. It's actually going up. And when that power increases, we're getting an intermodulation product between frequency A and frequency B, resulting here on top of my assigned frequency. Now, if you take a moment and go listen to this, and in this case, we're looking at VHF spectrum, so there's a lot of voice activity. What we hear is what we call the double the deviation product. Because we're looking at a 2F1 minus F2, the deviation of F1 is also doubled. And we can actually hear that if we go and listen on the intermod frequency or on the victim frequency. And the last case study is actually about coverage problems. And in this particular case, we're talking coverage problems of an FM broadcast station. So your average FM broadcast station is about 250 kilohertz wide. We know that the frequency band is 88 to 108 megahertz here in North America. and that frequency band has been in use for a long time. We know that there are several modes of operation for an FM broadcaster. We could have mono, which is, non-stereo operation. And stereo would have left plus right, left minus right, plus any subcarriers that we might be transmitting. And then we also have high definition FM or IBOC, the in-band on-channel FM. Most modern spectrum analyzers have the ability to turn themselves into a general purpose drive test unit. And what we basically do there is that we can actually turn on an integrated GPS receiver and ask for a time-based or distance-based trigger. So we can specify that we'd like to take a measurement once every 100 feet or 200 feet, or if you wanted to take a measurement once every 500 meters, you could do that. And what we set up is a basic channel power measurement. In this example, what we want to do is mimic a broadcast receiver. So we're going to set up a channel power measurement with roughly the same bandwidth as the broadcast receiver and go along and map our channel power measurements. We're essentially doing what's called a received signal strength indication here, an RSSI measurement. Now when we go and graph that data, we can actually take the log file directly out of the spectrum analyzer. And in this case, we put it into a fairly basic georeference mapping program. And we can see here that according to the colors, there was a fairly large drop in the signal amplitude from this location here to this location here. This used to be a very complicated procedure for people to go through and map this type of measurements, but today actually it's fairly commonplace. There are even a bunch of freeware tools available, including Google, that'll let you map the data directly online. So where do you go for help? There are a number of very good resources available on the web to help you with interference and to learn about spectrum. In the United States, of course, we have the FCC site, and there's a treasure trove of information that's available there. Probably one of the most interesting aspects of the FCC database is the ability for us to go in and search for spectrum users in a given frequency range in a given geographical area. So if you're having trouble and you are using licensed spectrum, it's possible for us to go in and take a look around to see who might be close by to us both geographically and in frequency. In Canada, spectrum management and telecommunications is managed through Industry Canada. If you go to the Spectrum Direct website, they have something called the TAFL, or the Technical Administrative Frequency List. It offers nearly exactly the same services as you find in the FCC, just for Canadian assignments. Another really good site to go to get information on interference is the ARRL website. This particular group has been around many years, and they've compiled a great deal of information on interference. And of course, you can go to our website, and on our website we have a specific spectrum management landing page that has a number of documents that help people figure out mapping and interference hunting with various real-time spectrum analyzers. And now we can take some questions from our audience.
Okay, we're ready for the Q&A portion of the session today. We have a number of questions that have come in, and thank you very much, Robin, for a very informative presentation and a lot of resources listed there at the end. Please note the presentation will be archived and available later on the Microwave Journal website, so you can always refer back to it. And if you attended today, you also receive follow-up email with these slides. So the first question is, do you have some images of different signature modulations that you can show us?
Actually, I have a great deal of information which shows signature modulations from a DPX perspective or a regular spectrum analyzer perspective. I would say when you get the contact information back from Tektronix, please don't hesitate to contact either our marketing department or me directly, and I'm certainly happy to share those with you.
Okay, next question. Because of the multipath, the estimated direction will not be as accurate as it could be. How do you handle that?
Oh, that's a great question. And this person who asked this question obviously has some experience doing mobile DF, because multipath is the enemy in mobile DF. And quite literally, the only way that we can combat that is by keeping moving. So the trick is when we get down on the ground or we're outside and we're trying to do it, particularly in a metropolitan environment, is get as many lines of bearing as possible. Never rely on a low statistical population. You need lots more. And this goes back to one of my rules about direction finding, is that you can never have enough bearings in direction finding. I always need to get as many as possible. The other thing you got to be really concerned about, though, if you're in a metropolitan area and your victim receiver is up high and you're trying to direction find from down low, you are going to have less success. It's really important for you to have the same radio horizon as your victim receiver is, or at least as close as possible.
Okay, another question. Can real-time analyzers look at spans greater than their real-time bandwidth?
Real-time spectrum analyzers from Tektronix can look at spans greater than their real-time span with what's called our stepped DPX function. So basically, if you had, for example, a 100 megahertz span, but your spectrum analyzer only has 25 megahertz of real-time bandwidth, it's possible for us to step that 25 megahertz of real-time bandwidth in 4 steps to go across a 100 megahertz span. Now, the data won't be contiguous, but it will give you the same probability of intercept in each step.
Okay, great. How long can spectrograms record spectrum information?
Spectrograms come in a variety of flavors. And to answer the question more succinctly, I would say that in our real-time engine, we can collect real-time spectrogram data for about 8 hours in one particular display. In our portable spectrum analyzers, it's possible for us to fill up one display of spectrogram, automatically store that, and then collect another one. So quite literally, we have the ability to store spectrogram data for as long as you have hard drive space, essentially.
Okay, great. I would really like to thank you for a very informative presentation today. I think that ends our Q&A session here. And remember, this session will be available later on in the archived on-demand version. And we thank Tektronix for their sponsorship and Robin for his great presentation. Thank you.